Welcome back to this session on advanced machine learning and data analysis for the physical sciences. The aim today is to continue the discussion of autoencoders and also make this clearer, the link between the principal component analysis and autoencoders. And there's a reason for also bringing up the principal component analysis is that that is one of the entry points for unsupervised learning. So autoencoders and what is going to come now, they generally fall under the class of unsupervised learning algorithms. And then at the end, we are going to look at codes. So we are going to look at several types of autoencoders. We can do autoencoders with a standard neural network. So we can have a pretty shallow under autoencoder. We can have undercomplete autoencoders. We can regularize them. We can look at the sparse autoencoders. We can use convolutional neural networks as a neural network in the autoencoder. There are denoising techniques, and there are also the possibility to have recurrent neural networks as a neural network inside the autoencoder. And the codes which we have here are codes which then can be used in the analysis of these differential equations which we have at hand in the project description. So the kind of idea is that we move from a general neural network to a recurrent neural networks, which we discussed in the previous weeks, and then we move to autoencoders. And autoencoders will also serve as a stepping stone towards other types of unsupervised learning methods, which are normally called generative methods. And these methods are more based on a probability distribution. And that allows us also to make a link with what is normally called Bayesian statistics. Now, you have probably received an email with the update for the rest of the semester, and we are going to run in this mode for the rest of the semester, which means that if you look at the schedule which we have, and you go to the official page, web page for the course, Physics 5421, just a quick reminder of that, and you click on schedule here, then you will get the plans for the rest of the semester. So if you scroll down, after the discussions which we've been having on autoencoders and links with the principal component analysis, you have, by the way, access to the Jupyter Notebook, the same which I'm going to run through the lectures today. Then we have the next topic, which is going to deal with the deep degenerative models. And these are normally called energy-based models because they will be inspired by a distribution function or probability distribution, which is going to be given by the so-called Boltzmann distribution. And that forms the basis for topics like Boltzmann machines. It means that we will need to revisit some topics of Monte Carlo Markov chain methods. And we have also the final topic, which is going to deal with generative adversarial networks. And we're going to spend some time on discussing Boltzmann machines. And this serves also as a kind of bridge towards Gaussian processes. So if we get time, we will say something about Gaussian processes as well. Now, Boltzmann machines and these GANs, they form one of the very active research fields nowadays. There is also an extension of autoencoders, which we are going to look at today, which is called variational autoencoders. And that is a topic which will also be discussed in the weeks after the Easter break. So next week, we are going to look at the basis for many of these deep generative models. And then we move over to Boltzmann machines and GANs. And then this will wrap up the part on unsupervised learning, which we have been started now. So if we go back to the Jupyter Notebook here, what we discussed last time was a little bit about the basics of autoencoders. And these are typically set up in terms of a decoder part, which takes the input data and it feeds it into an intermediate layer. And this layer feeds then its output to a decoder part. And the whole idea is that this decoder part is the one which we want to learn as much information as possible about the input data. So hopefully the so-called autoencoder, they are meant now to allow us to find information about the input data. So if an autoencoder succeeds in simply learning the input data, then it's not especially useful. So what we design the autoencoders for is actually to not copy perfectly the data which we have, but they are often restricted so that they copy only the data approximately. And then the hope is that the model is then able to, from this copying process via the decoder, that it's able to extract useful information about the data set, which we then can use in a unsupervised learning context. So the data are normally not labeled. And the modern autoencoders, they also have some very interesting properties, that they have a strong connection with stochastic interpretations, and again then Bayesian statistics. And this is something you will see very clearly when we move over next week to generative models. So that these are models which actually generate new input data. So autoencoders actually belong to this type of data of generative models. And the basic structures is that an autoencoder is typically a neural network where the outputs are its own inputs. And they're normally split. And if you go back to the whiteboard notes which you had from last week, into an encoder part, which maps the input via function f. And then there are some weights here which we need to train. That's the encoder part. And then it feeds it into a so-called code part, or the intermediate part, which produces an output. And this output is then fed into the decoder part via its own parameters. So there will be a weight function here. And the idea is to minimize the so-called construction error, which is the difference between the input x and this output which we produce, this x tilde here. Now, one of the things which we started with last week was actually to assume that there is a linear dependence in these functions, so that there's a linear dependence on the unknown parameters w multiplied with the input x, and we haven't specified whether these are matrices or vectors. In general, you could think of x as an input vector and w as a matrix of weights. And then we would now have a totally linear behavior. And when you do that and you construct the mean squared error, you can then think of this as the reconstruction error which you want to optimize. So by this kind of approximation, we want to have as small as possible difference between the input and the output from the decoder. And the hope then is that by obtaining these weights in the matrices V and W, that this can teach us something about the data which we have. And hopefully that can be used in the data analysis later. Now, what we did last week was actually to discuss or start discussing the principal component analysis, because what you have here, if you think of this linear behavior and this reconstruction error, this is nothing but the dimensionality reduction which the principal component analysis gives us. And the reason why I spend some time not only on autoencoders, but also on the principal component analysis, is that the principal component analysis is a dimensionality reduction method. And what I'm going to do now is to go through on the whiteboard a little bit more the mathematics behind the PCA, and link that back again to this reconstruction error, which you see here. And hopefully in that way, you see clear the effect of an autoencoder as a dimensionality reduction recipe, which is one of the main overarching themes for why we do machine learning. So you can think of machine learning as a way to reduce the complexity of a multidimensional problem. And hopefully by this kind of linear approach here, we obtain some deeper information about the data which we have, and this would now be encoded in these weights V and W here. So typically, an autoencoder is composed of shallow neural networks, but as you will see later, we can replace a neural network with a recurrent neural network, and that will fit very well in connection with the discussion of the project which we have, which deals with differential equations and in essence time series. So what I'm going to do now is to go back a little bit to the basics of the PCA and just go through some of the mathematics there, and then show you that when we take the PCA, that corresponds to the same as the autoencoder with a linear relation between the decoder and the encoder, and where these V and Ws are the weights of a neural network. And they are trained by the standard backpropagation algorithm. You can also have nonlinear relations, and that leads to a connection with the nonlinear PCA, or kernel PCA, as it's also called. So let me switch back to the whiteboard here after these introductory words. So let's just bring up that. So what I want to do now is to bring up this connection between the principal component analysis and autoencoders. And as I said, one of the reasons why we do that is that principal component analysis is one of the standard methods by which we can reduce the dimensionality of the problem. And it's linear algebra based, or you can derive it from a statistical interpretation. We are going to start with a linear algebra based method, which links with the singular value decomposition theorem. And we started to discuss some of these topics last week. So let's now look at the basics of the PCA, principal component analysis, PCA. Now, what we have is a data set which is given by a matrix, and we call this the design matrix. And this is a matrix of dimensionality n times p, and n is the number of samples. And you have seen this many, many times before. And P represents the number of features which we have. And if you're looking at, let's say, typical cancer databases, then features could be the thickness of the tumor, it could be the surface of the tumor, it could be the area of the tumor, etc., etc. So these would be typical features. And the samples would be the number of patients you have sampled. Now, the quantity which is important here is the covariance. So what we often also do is to rewrite X in terms of its vectors. So each column here represents a feature. So we just rewrite it like this. So we have an X1. So these are now vectors. And this goes all the way up to the final feature, P minus 1. These need not to be orthogonal. There can be linear dependencies. And this is what the covariance measures. So the covariance, cov, between two variables, xi and xj. So these are the two vectors which we have here. This is normally written in terms of a sum over k. And this has now the specific matrix elements for vector I. So think back, if you now look at one of these vectors which we have here, one of these. So this vector x of I is actually a column which now has x0 of I, x1 of I, and all the way down to xn minus 1 of I. So the covariance is then given by the mean values of these vectors. So x of I is just the mean value. So let me just remind you of that. So that would be a sum over 1 over n, and then you have a sum over k, and then xk of I. So these are the mean values. And this is multiplied with xkj minus xj. So we are not assuming that these mean values are the same. So it's common also to scale the data. Note also that I'm putting 1/n here. If you go into NumPy, you will see that that calculates the covariance with 1/n minus 1, because these expectation values, the mean values, are not properly determined. I mean, we don't have the exact mean values. So that gives a bias in the calculation of the covariance. But I'm just going to put n here, assuming that we have a large data set. So it's normal to scale the data. And here and from and on, I'm actually going to use the scaled data here, kx minus x of I. And this is normally what is also done when you calculate the quantities which are coming now. We are always dealing with scale data. And I'm going to be a little bit sloppy here in the notation, because I'm going to bring this back to xk of I. So if you just take a simple example, if you now suppose you have a design matrix X, which is a 3x2 matrix, so you would have now x00, x10, x20, and then I have x01, x11, and x22 here. These would be the typical matrix elements, and we would rewrite them in terms of this x0 and then x1, like this. And if I take the covariance between these two quantities of x0 and x1, this is obviously just the sum of 1/n, and I have k, and then I have this xk of 0 multiplied with xk of 1. And this is just a number. So this is a number of the in the covariance matrix, which means that when I write it out, this is nothing but 1/n, and then I have x00, x01, plus x10, x11, plus x20, x21. And we can rewrite this as a vector, transpose of a vector, of the column vector, multiplied with x01, x11, and x21. Sorry, this should be x21 here. x21. And this is again written as x0 times x1, x transpose, and that's the covariance, multiplied with 1/n. So we can now rewrite everything in terms of the matrix, the matrix X. So if you now look at what we have here, we can then define a covariance of the matrix X, and that is going to be given by 1/n, and with the transpose of the matrix times X. Now be careful now with the notations which we have, because I'm going to set X where I have the features along the rows and the features as column elements and the samples as the rows of a matrix. And that's why I now have X transpose times X. So these are not vectors any longer. This is the matrix X itself. So this is the design matrix. And you will see now that when you set it up here, this is going to give you the different covariances. And in our case now, for this specific matrix which we have, this example which you see here, that means that the covariance then, covariance of X, is going to be given by 1/n. And then I'm going to have here, I will have x0 times x0. I'm going to have x0 times x1. And then I'm going to have x1 transpose times x0. And then I will have x1 transpose multiplied with x1. So, and that's the matrix which I'm going to deal with. And remember now that X transpose times X, these are vectors, what you have here. So I hope you see the difference between this quantity. This is a matrix, and these are vectors. So the quantity here is just a scalar. And if you look carefully at what we have here, this is nothing but 1 divided, or let's just rewrite it like this. So this is the same as the variance. And then I have a sigma 1 squared. And then I get here the covariance of x0, x1. And here I have the covariance. So this is actually a symmetric matrix, like this. Any questions so far? So yeah, go ahead. Any questions? Okay. Yeah, I couldn't. No, there doesn't seem to be any questions here. So we just have to be a little bit careful with the way we define the matrices here. So in our case, we will have the samples as the rows and the features as the column elements. And we are now taking the covariance between different features in order to find correlations between features. So if you have a covariance which is different from 0, that means that there are some specific correlations between the data sets. And then you can divide this by the variance and define the so-called correlation matrix. So it's common to also deal with the correlation matrix because the covariance and the variances can take large values. But if you scale it, so you would actually take the covariance of x divided by the variance of x of I and divided by variance of x of j here. So when we're now looking at the two specific matrix elements, so let me just correct that one, because that's this is going to be proportional to the covariance between these two vectors. And you see now that if you have a diagonal element with xi and xj, this simply reduces to 1. So the covariance can be used then to define the correlation matrix. So in this specific case, the correlation matrix X for this 3x2 matrix, which we have, that would have 1 here. And then I would have the correlation, and I'm going to write it like this, of x0, x1. And here I have correlation of x1 and x0. And then I will have 1 along the diagonal. So often people actually deal with that specific matrix. So this is the correlation matrix for the design matrix. And what you have here is the covariance matrix for the design matrix. So just keep in mind that when I use this kind of notation here, I'm thinking now of the matrix. So this is the covariance matrix. And the matrix elements are given by the specific covariances or the variances along the diagonal. So this is now the quantity which we are going to look at. Now, there's an interesting thing here. If you think of the singular value decomposition theorem, because we can link the singular value decomposition. So let me quickly remind you of the singular value decomposition. We can rewrite a matrix X. This is our design matrix or feature matrix in terms of an orthogonal matrix U multiplied with a matrix which contains the singular values and multiplied with a new orthogonal matrix. So in our case, U is a matrix of dimensionality R of n times n. This matrix sigma, which contains the singular values, is a matrix of dimensionality n times p. And this matrix V has a dimensionality of p times p. So this is the singular value decomposition. And you can actually decompose any matrix, also singular matrices, in terms of the singular value decomposition. So this is something, it's actually a very powerful theorem and a powerful method because it allows us to decompose a matrix, and then we can analyze the matrix in terms of these different matrices which make up the singular value decomposition. So these matrices are orthogonal, or they can be unitary if we have complex matrices. And this is now given by the identity matrix with dimensionality n times n. And then I have V times V of t, which is equal to V of t times V. And that's the identity matrix of dimensionality P times P. And this matrix sigma is a matrix where we have these singular values. So I'm going to call them lambda 0, lambda 1, down to a lambda of P minus 1. And then the rest of the matrix elements can be 0. And typically these values, lambda 0 they are sorted so that lambda 0 is larger than lambda 1, lambda 2, and this goes all the way to lambda P minus 1, which is larger than 0. And then the remaining values are 0. And this matrix is often rewritten in terms of two blocks. One, a matrix where we have only non-zero elements, and then a set of 0 elements. And where I haven't specified the dimensionality of these matrices. And this matrix sigma, this has actually dimensionality of just P times P. That's important to keep in mind. And that defines normally the rank of matrix. So the thing which is interesting for us now, when we look at this covariance, X, which is given by 1 divided by n of this xt of x. So this is the design matrix. We can write this out in terms of the singular value decomposition. So this is 1 divided by n. And then I can rewrite this as a v times a sigma transpose times u of t times u times sigma times v of t. And that means in turn, since we have the orthogonality relation between the matrices u here, that means that we can rewrite this as 1 over n. And this is given by this matrix V times sigma t times sigma times V of t. And that's a matrix of dimensionality P times P, as you can easily see. And we know that the covariance has that dimensionality as well. And now comes a very interesting aspect here. So if we now look at this matrix X times T times X, if we take away the 1 over n term, just to make life a little bit simpler, so we can rewrite that in terms of the singular value decomposition. And we have these orthogonal matrices, V, and then we have this matrix sigma, which just has elements along the diagonal, and these are the so-called singular values. If I multiply with V from both sides, from the right, so if we do that, with V from the right, what we get then is that we have x of t times x multiplied with V, and that's equal to V times sigma t times sigma, and then I have V of t of V, and this is just the identity matrix. So this becomes equal to V times sigma t times sigma, which I'm going simply to write as sigma squared. And in our case, this sigma squared is just going to be given by this matrix sigma tilde, which we have here, because it's a P times P matrix. Now, this is actually very interesting because it tells us now the following, that the eigen, if I now take a component V of I, so this V is an orthogonal matrix, which has orthogonal vectors. So V0 is orthogonal to V1, etc., up to V of P minus 1. So that means that if I now take x of t here times x and multiply that with one of these vectors, V of I, this is going to be given by V of I times this value lambda I squared. So what we see now, if we multiply this with 1 over n and multiply with 1 over n here, what we have then is that we have xt of x, 1 over n, and this is nothing but the covariance matrix. So this is our cov x, the matrix, multiplied with V of I is equal to V of I times lambda of I squared. And this is nothing but multiplied with 1 over n So this is nothing but an eigenvalue problem where we have the eigenvalues, which are given by the singular components, lambda y divided by n. Okay, so this is actually very interesting. Now comes another interesting part here. So if I look at my covariance matrix, so the covariance matrix, if I take that one, my cov of x.
You know that the expansion of an operator, we have.
Oh, guys, could you unmute yourself here? I see where somebody here is not. Somebody needs to be muted here.
Do that expansion, that it converges and then you can.
So let me just unmute that participant here. Okie doke. Now it should be okay. Okay. So if you now look at the covariance matrix which we have, we know that we can, if we take this matrix, we can always find a transformation which diagonalizes that matrix. So the covariance matrix, the way we think of that, this is just the expectation value. So it's often written like this, E. If we take away the term N, it's this quantity here. If I now assume that I have a deterministic transformation, so I have a matrix S, and I multiply it with my covariance matrix of S here, this is something which I can rewrite. And since this is a deterministic matrix, it means that I don't need to put that one in the expectation value. So we could think of being able to diagonalize that one. And these values which we would get along the diagonal, we can label them as sigma 0 squared and down all the way down to sigma of p minus 1 squared. So we can always find such a matrix which diagonalizes the covariance matrix. So this is also an orthogonal matrix. It's a unitary matrix. And what we have done now is to perform a similarity transformation of the covariance. So what we have then is that with this specific transformation here, we have now an expectation value of S of t times x of t times x times s. And since these are deterministic matrices, when we perform an orthogonal transformation here, that means I can rewrite this in terms of the expectation value of xt times x multiplied with s. And this is just the covariance of a new variable y, which is diagonal. So what we are getting then is a new matrix, which is diagonal. And that specific matrix is nothing but the covariance matrix or the variance. So what we have in this specific case is where we say that this quantity is uncorrelated because we have performed a transformation. So this is an uncorrelated matrix. And this uncorrelated matrix is diagonal. And being diagonal means that what we have along the diagonal, so along the diagonal, what we have then is just a variance. Along the diagonal, we have just the variance. It means that the eigenvectors of this matrix, they are actually linear combinations of the different features. But when we perform the transformation now, what we get is a new matrix, which is just diagonal, and we interpret these diagonal matrix elements as the variance of the covariance matrix Y. So with that, we have the variance. We have the variance of this matrix of Y. And this variance is now going to be ordered so that we have sigma 0 divided by n, which is larger than sigma 1 divided by n. etc., up to sigma p minus 1 squared divided by n. So this is a variance which we are calculating. And if we now make the comparison with the singular value decomposition, if we go back here, you could now think of, if we add this factor of 1 over n, we know now that the eigenvectors of this matrix here, this matrix problem, this is an eigenvalue problem which you have here. The eigenvectors are the matrices of the orthogonal transformation resulting from the singular value decomposition. So this eigenvectors S, which we have here, so this matrix S, which we put up, is now a matrix which has a series of orthogonal vectors which result from the orthogonal transformation. And we have an SP minus 1. And this matrix S is simply equal to V from the singular value decomposition. As long as we identify the matrix we are decomposing now as the covariance matrix, and the eigenvalues, which we get from the, or the singular values, as the variance of the covariance matrix. So that means that these eigenvalues, which we put up here, this lambda 0 divided by n, they are the same as the sigma 0 divided by n, which means that what we have is that we have the eigenvalues lambda of I of n from the singular values. They are equal to the variance of the covariance matrix, from the covariance matrix. So this is actually a very interesting property here, which means that what we have done now is to have a variance of y0, which is larger due to the ordering of the singular value decomposition of y1, etc., up to larger than the variance of y of p minus 1, which is the last feature. Now, what the PCA theorem states is that there is an optimal dimension, m, which is smaller than the number of features. And often we want this m to be much, much smaller than the number of features. And we can use that one actually to set up a cutoff. So the PCA theorem states that there is an optimal dimension that we can define an optimal dimension which I'm going to call m, which is smaller than the total dimension of the problem. And if you have millions of features, this is clearly something which is beneficial. So often what you want to have is m much, much smaller than p. And we can use that one to define, so you can define a cutoff, which then defines a cutoff in terms of the variances. So what we would typically do then is to perform a summation over I equals 0 up to m minus 1. And then we have a sigma of I, the variance, which then is smaller than a specific cutoff variable which we choose. That could be 90% of the total variance. It could be 95% of the total variance, etc., etc. So if many of these features are not very strongly correlated, we can actually often just omit them and just keep the dominating features. So what we assume then is that there exist some features which are the dominating one, and we can use them to actually construct a reduced dimensionality. So this leads to reduced dimensionality. Now, with this, we are now ready to start to make the link between the principal component analysis and what an autoencoder is doing when we simply have this linear transformation, which we mentioned in the beginning of the lecture. So let's now look at the PCA approach, or the PCA theorem itself. So what we are going to assume is the following. We assume that there is a vector which we can start constructing a variance with. We assume thus that we have a transform, so a kind of transformation. We assume there is an orthogonal transformation, or an orthogonal transformation. And we assume that this matrix exists, S of t, equal to ST of S, which is a unitary matrix. And that contains now these different vectors. And we are going to construct the final variance based on iterating on these vectors. So we can assume now that we have these different vectors, S up to P minus 1. We now assume that this S0 of t times S0 is equal to 1. In principle, we are assuming that it's smaller than a large number. So we can assume that now it has been normalized. So what we define is a Lagrangian with a constraint. And then we want to optimize this quantity in terms of this vector S. And this Lagrangian is now given by a transformation, an orthogonal transformation. So I multiply this S0, which is a vector now, with my covariance matrix, the original covariance matrix of S, plus this constraint lambda 0. So this is a Lagrangian multiplier, minus the constraint, which is now S0 transpose times S0. And now I want to optimize this problem here. So I take the derivative with respect to S0, and I take the derivative with respect to lambda, which is what we typically do when we now want to optimize a problem. So we now optimize the Lagrangian, optimize with respect to S0 and lambda 0. And that is going to give us two equations. And you see, if I optimize this with respect to S0, so then if I take that one, what we get is the following expression. So now keep in mind that we have variance, the covariance, which is a matrix, times a vector. So this reduces simply to sigma 0, S0 equal to this Lagrangian parameter, lambda 0, times S0. So this simply states that this S0 is an eigenvector of the covariance matrix. And if we multiply that with S0, then we have simply back, if we now multiply, by S0t, what that simply means is that S0t times the covariance of X multiplied with S0 is the same as lambda 0. So this is an eigenvalue problem. And we know that from the SVD, this S0 is actually given by this eigenvector, or this orthogonal vector V0. So that means that this S0 is now the first eigenvector of this covariance matrix. So then we can construct the eigenvector problem in this specific way. We know that lambda 0 now, if we take the derivative with that one, we simply get back the other equation that S0 transpose times S0 is equal to 1, which is pretty obvious. So from this, we can now define lambda 0 as an eigenvalue. So this is the eigenvalue, which again is the variance of cov X for sigma 0 divided by n here. So that's the first parameter which we have. And the next thing we can do now is to find the second principal component. So this would be this S0 now is the first principal component. And we're assuming that this is the largest variance. Principal component. We can now construct the next principal component, the next one, which we call S1, and then we're going to take a small break here. We would construct that one with a constraint, obviously, that S1 transpose times S0, so they have to be orthogonal on each other, should be equal to 0. And that will give us a new Lagrangian, which is going to be given by S1 transpose times the covariance matrix of X times S1 plus, and obviously it has to be orthogonal. So 1 minus S1 of S1 and plus a new Lagrangian parameter, gamma, of S1 transpose times S0. And then we optimize or take the derivative, take derivatives, and this is where we stop now, and then we take a small break with respect to lambda 1, gamma, and S1. And when we do that one, we are going to find that this S1 can be interpreted as a new eigenvector, and we're going to get an eigenvalue lambda 1, which is going to be the variance for the eigenvector S1. And we are going to see that this gamma can then be defined in terms of the equations which we have here. And with that, we can, by induction, we can construct all the other eigenvectors by starting with these Lagrangians, where we just impose the orthogonality relations. And this is just another way of just reconstructing what we did with a singular value decomposition. So all these vectors S which we have, they are going to correspond to the vectors which we get from the orthogonal matrix, from the singular value decomposition. So what we're going to do also after the break is to show that we can now take one of these vectors S0 and then simply project out a solution. And this solution which we project out is going to be used to construct the so-called reconstruction error. And we will show that the smallest reconstruction error is the one which corresponds to the largest variance of the covariance matrix. And then we have the link between the PCA and the variance, and the largest variance is the one which we are interested in keeping as a way to truncate the dimensionality of the problem. And when we set up this reconstruction error, this is going to be the same in its mathematical form is going to be the same as the one we had for the autoencoders when we have a linear dependence. So sorry for going a little bit over time and going a little bit fast through these things. You will find also the same material in the lecture notes. So after the break, we are going to link this PCA way of thinking with the dimensionality reduction, which is also included in autoencoders. So if we look at this Lagrangian now, which has a constraint on both the vectors S1 and S0, what we can do now when we take the derivative with respect to S1, so just keep in mind that when we take the derivative with respect to S1, it's actually this term which is being affected and this term. Now these are vectors, but if you think back to scalars, it would be S1 squared. So these derivatives are going to give us a factor of a half. And I just divide out that factor of a half. And if I look then at the final derivative with respect to S1, so if we take that one, we are going to get the following expression. We are going to get the covariance of X multiplied with this S1. And then I get plus, and I've divided away the factor of a half. So gamma divided by 2 multiplied with this vector S0, which we have already defined from the previous optimization of the Lagrangian. And then we get in addition a term which goes like minus lambda 1. So we can actually rewrite that one in terms of a lambda 1 multiplied with S1, because we're just putting that derivative to 0. I mean, the other two derivatives are pretty trivial because they are just going to give us S1 transpose S0 with respect to gamma equal to 0, which is what we put in as a condition. And similarly, we have the same condition for the derivative of lambda 1. But it's this expression here which is interesting for us now. So if I multiply from the left, with the transpose vector S0, then I know that S0 multiplied with the covariance of X. If I just look at this term, this is nothing but this eigenvalue lambda 0, which is the variance, multiplied with S0. And then I have times S1 plus a factor of gamma divided by 2 by S0 transpose times S0. And we have already defined this one to be equal to 1. And this is going to be equal to lambda times S0t times S of 1. And we know that S0 transpose times S of 1 is also a quantity which we want to set to 0. If we don't do that assumption, what we have now is the following. We get that the gamma has to be equal to the factor of 2 times lambda 1 minus lambda 0. And this is multiplied with S0 transpose times S of 1. Now, we have assumed that lambda 1 is not the same as lambda 0. So the only thing which we can use then is that this one is equal to 0. So that means that this term gamma has to be equal to 0. And with that, what we end up with is actually that S1 of transpose times the covariance of X multiplied with S1 has to be equal to this lambda 1, which is the same as the variance of the transformed matrix. And this is the variance of what we call Y1, where this cov of Y, the new matrix, is given by this S, the similarity transform matrix X, multiplied with S here. And ST is now a matrix, whereas S1, when you see a subscript, these are vectors. So S1 is then the next leading vector of this covariance matrix, and it's restricted to be orthogonal, or the orthogonal complement of S0. Now, what you can do next is by induction, we can then find all the other eigenvectors here. So if we now look at further eigenvectors, we have the constraint that they have to be orthogonal, delta ij. And then we can construct and show that we are getting the variance. We construct all the other eigenvectors. So we get L, which is given by S of I multiplied with the covariance of X. So we can construct by induction all the other eigenvalues. And then we have an S of I plus the constraint we have on the vector that it should be orthogonal, minus S of I of t, and normalized to 1. And then I have the additional constraints for all the other ones, from 1 up, from I equals 0 up to I minus 1. And then we have a gamma of j multiplied with S of it times S of j. And then we can construct all the other ones by just using these relations here. And then we can show that the different eigenvalues correspond to the variances of this transformed covariance matrix Y. And with that, we have a recipe by which we can show that what we are getting is actually the variance of this specific matrix using these orthogonal transformations. So if you want to get a kind of intuitive understanding of it, if you now think of a two-dimensional data set, and this is the example which we looked at last week. Suppose now that we have a data set in terms of x1 and x2 here, which is very scattered along the x1, x2 representation. So these are the data points which we have. In this specific case, we would have a large variance in x1 and in x2. So large variance means that we have large deviations between the data points. This means that most likely for that specific case, we would have to keep these degrees of freedom. If we, on the other hand, have a data set which looks very much like this, so we have a large variance in one of the axes, x1 and x2 here. So we have a small variance, a small variation. So variance actually stands for the variation in x2 and large in x1. Then we could think of dropping, could then drop x2 as a degree of freedom. So DOF stands for degree of freedom. So the PCA is actually doing this. So what we have done now is to look at what we normally call the geometric interpretation in terms of the singular value decomposition. But there is nothing which hinders us from constructing these vectors in a different way. So in order to make a long story short, what I'm going to say now, if you now look at the reconstructed vectors which we produce and calculate the mean squared error, so we can now set up a reconstruction error. Reconstruction. And we are going to call this for j of x. And it looks like the mean squared error, except that now it's the mean squared error. So we're looping over the data sets which we have. And we have an x of I minus an x of I tilde, and this is squared. So this x of I tilde, this is our approximation to the data. And if we go back to the theory of autoencoders, so let's just make the link here. What we had then, when we had this linear dependence between the encoder and the decoder, what we had then is that this x of tilde, and now I'm writing this as a vector, could be written out in terms of a matrix which transforms the intermediate layers to the decoder, this matrix V, and then multiplied with a matrix W, which links the input with the intermediate layer. So this was a kind of linear dependence which we put up. And in that case, what we did when we think of the mean squared error, what we had then was an error for the autoencoder, which I'm going to call j tilde of x, which is given by 1 over n, and then I have this I equals 0 up to n minus 1. And then I have my x of I minus v times w, and now I perform the multiplication of these matrices and multiply it out with an x of I here. And this is squared. So what you can show now, and I'm not going to go through all the details here, but what we could think of is that we have produced a matrix where now we have a vector S, which is an approximation to this x I tilde x. So what we are assuming now is that we have, and this is the other variant of the PCA theorem. So we have a approximation where we take the vectors S0 and S0 transpose and multiply that one with our data set, X. And this is going to represent our X tilde here. So the only assumption we have made is that there is a basis S0 and S0 transpose, which forms a basis for an orthogonal transformation. Now, remember now that what this is not an inner product. This is actually an outer product. So that yields a matrix. Outer product of two vectors, that is actually a matrix. So if you now think of this S0 as a vector which has only two components, so we could have S00 and S10, then you see that if I take the S0 transpose times S0, then this is just the inner products, which means that we get S0 squared plus S10 squared. But if I take the outer product, so just to remind you of that, that is going to give us a 2 by 2 matrix, where I'm going to have S00, and this is multiplied with S0, so we have S0 squared. And here I'm going to have S00 multiplied with S10, and then I'm going to have S10 with S00, and then I'm going to have S10 squared here. So that's a matrix. Now, what we can do then is to show that, and this is the PCA theorem, with the reconstruction error. So I'm just going to state the theorem. So the PCA theorem from the reconstruction error gives us the smallest reconstruction error if this vector S0, if S0 are the eigenvectors of the covariance matrix with largest variance. Which we call sigma 0. So I'm not going to go through the details here. Actually, the proof is not that difficult. So when you maximize, or actually in this case, when you minimize the smallest reconstruction error, which is now this quantity which you see here. And in our case, this quantity is now going to be given. So if I take and maximize, so if I take, minimize argmin with respect to S0 of the quantity which is given by 1 over n, and then I sum over all the data sets which I have, and I now rewrite this. We can actually rewrite this in terms of a matrix vector case. So let's just rewrite it in terms of this. So if we now take S or X here, the vector X, minus S0 times S0 transpose times X, if I maximize this quantity here, then the minimal error corresponds to us having a vector S0, which is the eigenvector of the covariance matrix with the largest variance. So, and this is nothing but what we had for the autoencoders. And then so think of the autoencoder. The autoencoder with linear dependence. And there the reconstruction error which we have is an error of the following type, argmin with respect to the matrix V and the matrix W. So we have two matrices, which are multiplied, so that gives a new matrix. Remember now that this is the outer product, S0 times S0 transpose, so that's a matrix. And if you look at that one, this problem here, this is 1 divided by X minus, and then we have the matrix V times W times X, and this is a norm 2 squared. So if you look at the mathematics here, what we have is that V multiplied with W is now proportional to this vector S0 times S0 transpose. So I'm not giving you the full proof of the PCA theorem based on the reconstruction error. So PCA has there are two different ways of showing it. So one is from the geometrical point of view using the singular value decomposition, and that gives us a recipe where we now can put a cutoff in terms of the variance of the covariance matrix, which means that when we diagonalize the covariance matrix, we just keep those eigenvalues for the covariance matrix, which are the largest one, which correspond to the largest variance, and we put a cutoff there, which we have to decide upon. Alternatively, we can construct the PCA theorem from the reconstruction error, and the reconstruction error is us assuming that there is an orthogonal vector S0. We then construct the new matrix here, which actually projects out these components, and the model which we make then, so you can think of this as a model, and we take the difference between the data set we have and the model we have made with this orthogonal basis. And with that basis, we then can minimize the reconstruction error, and we can then show formally that these vectors S, they have to correspond to the eigenvectors of the covariance matrix. So the largest variance is, the state with the largest variance is the one which gives us the smallest reconstruction error. And then we can keep adding the different other vectors, S1, S2, S3, etc., till we have reconstructed the full sum over the variances. And the PCA deals actually with us reconstructing the data set by performing this set of orthogonal transformations. And if we then think of the autoencoder in its classical form, and we take only a linear dependence between the decoder and the encoder, then this is the same as basically the mathematics is basically the same as the one which we have in PCA. So you can think of autoencoders as a way to reduce the dimensionality of the problem. And the next thing which you could assume is that you could have a nonlinear dependence. And there is a whole literature on nonlinear PCA, so you can show similar relations with the nonlinear PCA as well. So the thing which I wanted to say a little bit about now is how do we actually implement these autoencoders, and what kind of autoencoders do we actually have? So there are several approaches to these, and the literature is actually full of them. And the interesting thing with the autoencoders also is that they can be linked with a probabilistic interpretation. So what I'm going to do now is to switch back to the Jupyter Notebook. So this was a digression with the PCA. And you would scale the data, you diagonalize the covariance matrix, or you can use the SVD decomposition. And when you diagonalize the covariance matrix, you would pick those eigenvalues which are largest, which correspond to the largest variance, and you would leave out the other features. So you could put a cutoff where you sum the variances up to, let's say, 95%, and you would leave out the contributions beyond 95%. And then you would simply say that these are the degrees of freedom which I'm going to keep. So that was a long story to bring the link between PCA as a dimensionality reduction method and the principal component analysis and autoencoders. The reason why I also bring up, as I said in the introduction, why I bring up the principal component analysis is that is a standard way of reducing the dimensionality problem. And it falls under the class of unsupervised learning methods. But it's essentially just a linear algebra approach where we diagonalize the covariance matrix. And if the data are not very correlated and we have some features with a large variance, we would just keep those features because they are most likely the features which are essential to define and to describe the data. And then we can just leave out all the other features. So what I wanted to say a little bit about now are different types of autoencoders. So one of the type of autoencoders which we have is, and this is often the most standard one, is a so-called undercomplete autoencoder, which means that the dimension of the decoder, so if we go back to the equations which we are setting up, so you could now think of the transformation from the data set to this intermediate layer, and you can think of that as being linked with a neural network. This data set here, X, is then transformed through this W and produces an output H. This output H is now fed into the decoder part. So what you could think of now is that the dimensionality of X tilde is much smaller than the dimensionality of X. And this aligns well with what we have been discussing when it comes to the principal component analysis. So the reason why you do that, so this is tightly linked if you have an undercomplete autoencoder. This is tightly linked with the same thinking as you had in a PCA. And what we are hoping for then is that learning an undercomplete representation that forces the autoencoder to capture the most important features of the training data which we have. And the learning process is then simply described by optimizing a function like the one we put up here, this one, except that now this X tilde has a much smaller dimensionality than the data set itself. So when we perform this operation here, the matrices V and W, they have a smaller dimensionality than that represented by the full data set. And then we would simply compute this can typically be our cost or loss function, and this would be the function which we would optimize. So the undercomplete ones are typical examples of the most common approach. And you can have nonlinear encoder functions, and you can have nonlinear decoder functions, and that would simply lead to a generalization of the PCA theorem as we discussed. You can have something which are called regularized autoencoders, but you can also have overcomplete autoencoders, which are less common. The regularized autoencoders is something we are coming back to when we are going to study Boltzmann machines and variational autoencoders and other types of generative methods. Another type of autoencoder which you will encounter in the literature is something which is called a sparse autoencoder. So in that specific case, what you would do then is to learn features for, let's say, another task. It's often used for classification. And you would add a penalty to the cost function, which is seen as a kind of regularization term, which is added to a feed-forward network. And the primary task is actually to copy the input to the output. So it's an unsupervised learning. And possibly also perform some kind of supervised tasks. And this is only going to depend on some sparse features, and which means in turn that with these sparse features, you are trying to reduce the dimensionality of the problem. So sparse autoencoders are also autoencoders which are being used quite a lot. We can have a denoising of the autoencoders, and denoising training that forces these functions f and g, which we put up here. So this function f here and g, it forces them to actually learn. So what did I had some notes here, which it encourages function to learn some specific data, and where our x tilde now is a copy of x that has been corrupted by some noise. And denoising the autoencoders is normally done in a way to actually undo the corruptions rather than simply just copying the input. So it forces these functions f and g to implicitly learn the structure of some probability distributions. And they provide another example on how you can try to construct a reconstruction error, which also has some added noise. So denoising autoencoders is a very common approach. So it means that it receives a corrupted data as input, and it's trained to predict the original uncorrupted data point as its output. So these are typical examples of decoders and encoders which you can meet. There's also quite a lot of research on stochastic encoders and decoders, which means that you try to find a probability distribution which links the input with this intermediate layer. And then you have a new probability distribution which links the intermediate layer with the decoder layer. So if you go into chapter 14 of this textbook by Cowell and Goodfellow and Benjo, you will find a detailed description of many of these encoder-decoder possibilities which we have. And you have the possibility to link or to replace a standard neural network with convolutional neural networks. You can do it with recurrent neural networks, etc., etc. So in the example codes, which you will find at the end of the slides here, after the discussions of the principal component analysis, is a set of codes which I have borrowed from the textbook by Aurélien Geron. And these are codes which we can easily transfer to our own case. So the first one is a typical linear autoencoder, which we have discussed now, where you have a linear dependence between the encoder and the decoder. And in this specific case, there is a simple data set which is being used. And that simple data set is now just given by some three-dimensional data, which are just generated by a random function times some constants. So this is not the most exciting data. So we have some random angles, and then we produce a data set in the X, Y, and Z direction in terms of cosines of these angles, as you can see here. And this is a training data, which is then used by the autoencoder. And in this specific case, you can see how we can implement this with Keras. You can define the number of layers in the encoder and the decoder. And you would then feed in the encoder and the decoder. So these are the layers, the neural networks which we have, which then connect the input with the intermediate layer, and then the intermediate layer with the output which we want to produce. And in this particular case, we simply produce the, as a loss function or cost function, we have the mean squared error. And this contains now a standard gradient, stochastic gradient descent with a given learning rate. And then you can make a plot of this and see how well that reproduces the data set, and also prints out the mean squared error which we have. So this is perhaps not the most exciting case, but it could serve as a basis for the solution of the differential equations which we're looking at. And in that case, we could simply use the differential equation solver to generate a data set instead of the data set which we have here. So our data set would now be the solution of the differential equation solver, which we have defined. And that could then be fed into the autoencoder model, as you see here in this simple case here. And so I invite you to actually try this out. When you have tested the recurrent neural networks and the standard neural networks for the differential equations, the next step in the project is actually to try to work out the autoencoder connection. So I would simply take this simple code which you see here and just use that one to test whether the autoencoders with this simple structure here with a pretty shallow neural network in the decoder and the encoder part does a good job or not. Now, in the examples which follow after here, we have cases with a so-called stacked one where we can have more hidden layers. The data set is now a slightly different data set, and it's a data set which has been used a lot in order to identify the type of, how to say, it's called a fashion data set, but it's actually you being able to identify whether you have shoes, trousers, t-shirts, or whatever. And in this case here, the activation function which is being used is a so-called, what is now? It's an exponential linear unit which has an addition. So I never remember what the S is. I have to come back to that one. It's actually one of the, it's an exponential linear unit, and then it has an additional parameter, and I think this S stands for that. And in this case, we have the cross entropy, so just identify what kind of wear you have, and whether this is a t-shirt, whether it's a shoe or whatever. And you can see the reconstruction here, and then you can see the original here. So this is actually doing a pretty job in reconstructing the data set. So you could now have some data set which you want to use, where you now have actually reduced the dimensionality. So you see you have a blurred image here, but you can still recognize this is a shoe, and this is a t-shirt, and I think this is a bag, and this is, I guess, is a dress here. And you can visualize it in different ways. So this would be a kind of cluster of where you have the data sets, and you would then visualize it in terms of shoes and boots and trousers, etc., etc. And so these different chunks here is how you actually have separated the data which you have in different categories. And this is the alternative to the MNIST data set with handwritten numbers, where you have replaced the handwritten numbers with different gear which you can wear, like trousers, boots, shoes, or whatever. You can repeat the same, and you can use convolutional layers instead of standard dense layers. And there's an example here, which I took again from the textbook by Geron. There's a long, actually, if you go to his GitHub address, you will find many of these examples. So I have simply borrowed those examples to illustrate how you can play around with decoders. In our case, however, what I would typically recommend is to get started with this simpler case where you replace this random data with the data which you generate from the solution of a differential equation. And then try that out with the simplest possible linear autoencoders. And then you can keep adding features to it. You can use recurrent neural networks in the autoencoders. So there's an example here which I took from again the same textbook, and this deals with the same data set, and it takes now a long short-term memory recurrent neural network. And in this case, since we are dealing with classification problems, it has the binary cross entropy here as the cost function which is optimized. And again, you see the same type of optimizers, stochastic gradient descents, etc., etc. Now, some of these can actually take a lot of time. There is also an example on how you can denoise the autoencoders. So I mentioned that denoised autoencoders is also an active research field, and it's one of the examples of which are well discussed in the textbook by Goodfellow et al. And this is still in this chapter 14. So if you wish to study a little bit more on these different options for autoencoders, I invite you to take a look at chapter 14. Next week, when we are going to look at the generative models, we will actually use actively from chapter 16 to chapter 20 in the textbook by Goodfellow et al. and they give a very nice description of these so-called energy-based models, which allow us to bring in this stochastic interpretation and to bring in Monte Carlo Markov chain methods in order to produce the different events which we want to simulate and data sets. Okay, so feel free to look at these examples. I haven't had time to replace the data set with the differential equations, but this is something which I would like to do in the next coming weeks before we have the Easter break. But I would say that with these kind of material here, which you see here, what you need to do is simply to replace your data with the data which is used here, which is just a random data over angles in 3 dimensions. So what you do have is actually the solution of a differential equation in 3 dimensions with x, y, and z. So that means that this is pretty close. This data set here would be pretty close to what you have from the simulations with the Lorentz attractor. Okay, so this is going to conclude my discussions of autoencoders now. I'm going to add more material to these slides, but next week I wanted to start with the generative models and energy-based models, which is going to lead us first to a repeat of Markov chain Monte Carlo methods and a discussion of Boltzmann machines, which will be our next type of machine learning method. And that allows us also to make a link with a probability distribution. And from that, we will look at generative models like these Boltzmann machines, different types of them, and general adversarial networks, GANs, and variational autoencoders. And then we should have a whole battery of different methods which can be used to also study the differential equations which we have at hand. So we are now entering the domain of unsupervised methods. And then after the Easter break, depending on how much time we have left, I wanted to say something about eventually Gaussian processes and Bayesian statistics, if we get time. Okay, this is going to stop today's lecture. And I'm going to stop the recording.